several courses in statistics and probability, and so what I plan to say in this four classes this week is to say how what you learned from my course will help you in the courses that you'll be taking in year 2 and in year 2 because I will not be teaching any of the year 2 courses, as you know. I only teach year 1 and year 3 courses, so I will be missing you guys a lot next year. I hope you too. I mean, as you know, I put in a lot of time and effort into teaching this course, and I hope excuse me, sorry. I hope that what you learned in this course will be useful to you in year 2 and later on. So, okay, before I go into that, let me say that this week we have 4 classes, and I would like all of you, well, if possible, of course, depending on what schedule you have, I don't know. So we have classes today. Today is Tuesday, right? Tuesday, 5th of May, 9 to 10 a.m. And we have class tomorrow, 6th of May, from 10 to 11 a.m. And then we have 2 classes on Thursday, 7th of May, from 11 to noon. And then also from 1 to 2 p.m. So if possible, I mean, I would like all of you to come to these classes. I mean, you don't have to, but I mean, because as I said, what I plan to cover in these 4 classes will be different. I mean, I'll try to go through different things that we learned in this course and will help you, or may help you in the second year. Now, in year 2, there are basically 2 courses that I think you may want to take. I think one of them is compulsory. In semester 1, excuse me, semester 1 of year 2, there is a course called probability 2. Probability 2. I don't know who's going to teach that, but I will not be teaching that, certainly. And then in semester 2 of year 2, there is a course called Statistical Methods. Right, and both these courses follow up on what I have taught you in this course. I mean, Introduction to Statistics to some extent. So, I mean, I will be teaching neither of these courses. I don't know who is teaching it, but somebody else will be teaching these courses. But what I like to tell you in the 4 classes we have this week is to what extent that these 2 courses you'll be taking in year 2 follow up from what I have taught you in this course, right? So let me start with the semester 1 course, which is on probability 2, right? Probability 2 will cover things like random variables. I know you already done random variables, discrete and continuous random variables, functions of random variables, and so on. But it will also cover like expectations. I mean, in this course, we talked about expectations, variance, and so on. But but I did not go into actually deriving any of the expressions. Like I gave, you may recall that in the on the first day of the classes, on the first day of classes, I gave you a handout with formulas for expectation and the mean and the variance, right? But I did not actually derive any of them. And one thing you will do in year 2, in the probability 2 course, is how to derive them. Like, so let me talk about that. For example, if x is a random variable, then then the mean of the random variable is denoted by the expectation of x. All right. This, I mean, I already talked about this in this course. And the variance is denoted by the expectation of x squared minus the expectation of x. Right? It's like this, right? And it's denoted by variance of x, right? Okay. And there are also, so the mean and the variance, they only involve the expectation of x and the expectation of x squared. But there are higher order moments that you will need to know. For example, there's something called the skewness. I'm not sure whether you're familiar. I mean, this you will talk about it in year 2. Skewness is a measure of whether the data or the random variable in this case is skewed to the positive or skewed to the negative, and is defined as follows. It's defined as the expectation of x minus the expectation of x cubed divided by the variance of x to the power 3/2. Right, this is the, it can be, the skewness can be positive or negative. So if it is negative, that means the variable is negatively skewed. If it is positive, that means it's positively skewed. And there's also something known as kurtosis. Kurtosis is a measure of peakness of the data, or of the variable in this case. The kurtosis is defined as the expectation of x minus the expectation of x to the power 4 divided by the variance of x squared. So kurtosis is a measure of, it tells you how peaked the variable x is. So in other words, if x is represented by a data, how peaked the data is when you draw a histogram, how peaked it is. That's what kurtosis says, whereas skewness is whether it's positive or negatively skewed, right? So each of these 4 measures, they involve, I mean, the first one involves the expectation of x. The second one involves the expectation of x squared. The third involves the expectation of x cubed. And the fourth involves the expectation of x power 4. And then there is the expectation of x to the power n, which is known as the nth moment. I think I briefly touched on it. And it's known as the nth moment of the variable x. So for example, when n equal to 1 is the mean, when n equal to 2, it can be used to compute the variance. And n equal to 3, it can be used to compute the skewness. And when n equal to 4, it can be used to compute the kurtosis and so on. Okay. All right, guys. So this is all this, and these are things you probably learn in probability 2 in semester 1 of year 2. But what I want, and also you will also learn about how to actually derive expressions for these measures. So in essence, deriving expressions for these measures will involve basically integration or summation. So for example, let me give you an example. Let me give you an example, maybe a few examples. Example 1, suppose x has the exponential distribution with parameter a, right? Okay, so in this case, I'm still getting emails about the summation. Sorry about it, guys. In this case, suppose we want to calculate the expectation of x to the power n. So because exponential is a continuous variable, you basically you need to integrate from 0 to infinity of x to the n and times the density of exponential, which is a times e minus x dx. Okay, so this is what you will need to do. Now to do this integration, you need to make a substitution. So let's say y equal to ax, right? So x will be y divided by a. So dx will be dy divided by a. So let me put this in a box. Okay, and then if you make the substitution, this is what you will get. So you get 0 to infinity of x will become okay. Okay, and this will become 1 divided by, and this integral I'm sure you should be familiar with. It's known as this. I think I introduced this in the course. I mean, in my course, which is the gamma function at n plus 1. And one property of a gamma function, you may recall, is n gamma at n plus 1 is n factorial, so divided by an. So this is the general formula for the nth moment. The nth moment of in this case, the exponential random variable, right? And so it can be used to compute the mean and the variance and the skewness and the kurtosis and all kind of things. So for example, if you want to find the mean, the expectation of x, you put n equal to 1, so it becomes 1 divided by a, all right? And if you want to find the, excuse me, if you want to find the variance of x, then you put, you use the formula okay, and this will become 2 over a squared, and n equal to 2, minus 1 over a squared. So this will be 1 over a squared. Okay. And then, and so on, like, and if you want to find the skewness, you can do similar things, like, you know, use the formula that I gave you earlier, which is this one here. This is the this is the formula for skewness and kurtosis and so on. Okay. So these clearly follow up on what we did in my course, because I mean I didn't focus on any derivations as such because it was not part of intro to statistics. So I mean in probability 2 it will be more on derivations than applications. So you should be prepared for things like this in probability 2. Okay, and so let me try to do a few. So this is example 1, example 2. Suppose your variable from uniform 0 to a. So in this case, the nth moment, the expectation of x power n will be equal to 0 to a, x to the power n, times the density of this, which is 1 divided by a dx. Okay. And if you do the integration, you get x to the n over n plus 1. And take the limits, you get 1 over a and this becomes a to the power n divided by n plus 1. All right, so this is the nth moment. And once again, you can use this to find the mean, variance, and so on. So for example, the mean, you put n equal to 1, so it will be a divided by 2. And to find the variance, you put you use this formula here. And if you work this out, it will be a squared divided by 12. Okay. Similarly, you can do the skewness and the kurtosis, right? I will leave them for you to do. Let's also let's see if we can find like a discrete variable. So far, the two examples I've done are both on continuous, right? For discrete, so let's say example 3. I'm trying to think about a discrete distribution. Well, it's not easy to find one, but which has a closed form, x to the power n. Trying to think. You guys okay? Suppose This is the Bernoulli run. I'm sure all of you know the Bernoulli random variable, which takes only two values, one with probability p and 0 with probability 1 minus p. So in this case, if you want to find the expectation of x to the power n, you need to do the sum, right? So it's gonna be 1 to the power n times p plus 0 to the power n times 1 minus p. Right, so the answer will be equal to p. So the expectation of x to the power n is p, right? And the expectation, so if you put, if you want the mean, for example, which is the expectation of x, you put n equal to 1, which is p. And if you want the variance, use this formula here. Yeah, and this will be p minus p squared, which is p times 1 minus p. Okay, guys, so these are three examples on trying to find the nth moment and using that to find things like the mean and the variance and the skewness and the kurtosis, right? And this you will, this clearly follows up from what we've done in my course, and it will be useful for you in year 2. Another thing you will learn in probability 2 is about generating functions. I don't know whether you came across this before or not, but generating functions. Generating functions is again a concept that can be used to derive properties of a random variable, right? So, for example, suppose you have a random variable x, right? And you will talk about in probability 2, you will talk about 3 different, at least, maybe more, I don't know, depends on who teaches it, but the 3 different generating functions. The first one is called the moment generating function, or MGF, which is defined by the following, is usually m of t equals to the expectation of e dx, right? This is the definition of a moment generating function. And as I will explain in a minute, this function, this is a functional. It can be used to derive moments of a random variable. So for example, right, it's not difficult to show, for example, the expectation of x. I'm not going to prove it because you will prove it in year 2 when you go to year 2. It can be proved from this that the expectation of x, right, is equal to the first derivative of m of t, then at t equal to 0. And it can also be proved that the expectation of x squared it's a second derivative of m of t at t equal to 0, and so on. And so on like this. So that's known as the moment. The reason that's why it's known as the moment generating function, because of these properties. Okay. Now, another thing that you will learn about in year 2 is the probability generating function. Is denoted by PGF, defined by the following. Just give me a second. Let me get the definition right. Sometimes ago, okay, it's defined by the following notation: G of t equals to the expectation of t power x. Yeah. This is known as the probability generating function. Now, the reason that is known as the probability generating function is because of the following. It can be shown that from this, right, that the probability that x equal to, say, a variable, say a number k, right, is equal to 1 over k factorial times the kth derivative of g of t at t equal to 0. So this is exactly because using this functional, you can derive the probability that x equal to k, right? Because that's why it's known as the probability generating function. And number C, A, B, and C. Okay, the C is the most important of the three. It's known as the characteristic function. Characteristic function is denoted by CF, defined by normally people use this notation, phi of t. I mean, some people use a different notation. It's defined by E, the expectation of E I T X, right? Where I is the complex number that is square root of minus 1. Okay, guys. So these are, these are three functionals you will talk about, because each has its own meaning. Like the first one, which is the excuse me. The first one is the moment generating function, can be used to compute moments. Let me try to go back to it. Where is it? Yeah, here we are. The first one here, yeah, it can be used to compute moments of a random variable. The second one, the PGF, can be used to compute the probabilities of a random variable. The third one is characteristic function. Is okay. The meaning of this one is characteristic function is very useful, because for every random variable there's the correspond. You should know a characteristic function of a random variable. You know the distribution it has, right? So I should try to like this. So what I'm saying is that for given a random variable x, the corresponding characteristic function is unique. So in other words, if you know the characteristic function of a random variable, you know everything about it, including the density, distribution, etc. Okay. So the random variable is uniquely determined by the characteristic function. Okay. All right, guys. Any questions so far? I know this is nothing to do with my course, but this is, I'm just trying to help you guys for when you guys go to year 2. Yeah, these are stuff you will learn about in year 2. So I'm just trying to help you guys on how to, you will feel, relieved to know some of this before when you go to year 2. So let's try to do some examples. So suppose you have a random variable x following the exponential distribution. So let's try to derive each of the 3 things that I talked about today. That is the MGF, or the moment generating function, PGF, the probability generating function, and finally the characteristic function, which is the CF. Okay, so let's start with MGF. All right, so MGF is this one, right? So this will be equal to integral from 0 to infinity of E gx, and the density of the exponential is A times E minus AX dx. Okay. Now if you pull the constant A out, this will be 0 to infinity. Okay, guys. So this is now the integral of this is straightforward. So you have okay. Now limit at infinity is 0 if assuming A minus t is positive, and the limit at 0 is this one. Okay, so that's provided if, I must say, if A is greater than t, and this becomes A divided by A minus t. This is the MTF for the exponential random variable. Okay. Right now, let's try to find the. Excuse me, where am I? By the way, if you have any questions, just try to use the chat box or try to use the microphone if you have one. Okay. The second thing is the PGF, which is defined by the expectation of t raised to the power x, right? Okay. So in this case, it will be integral from 0 to infinity of t power x a e to the minus ax dx. Okay, guys. Now, how do we integrate this? Any ideas, guys? Doesn't look. I'm trying to think. Sometimes I don't know. So, exponential. Oh yeah, you can pull out the a outside. So you have integral from 0 to infinity of t to the power x. You can write as e to the power log of t times x, right? Then you have minus ax dx. You see what I've done? I have written t power x as I have written t to the power x as this, right? Now this you can write as follows. Okay, you can write this as follows. Okay, now integral of this is not so difficult. So let's see what we get. So we get right. All right, now at infinity, if you assume that a is greater than log of t, the limit is 0. And at 1, it will be 1 divided by minus of a minus log of t. Right, that's once again assuming that a is greater than log of t. Okay. So this becomes a divided by a minus log of t. So this is the probability generating function, exponential random variable, and this can be used, as I said before, this can be used to derive probabilities associated with the exponential variable. Okay. All right, that's part B. Now part C is to derive the characteristic function. So it's phi of t. Okay. So this will be this is the definition. Remember, the I in the characteristic function denotes the complex number square root of -1, right? So you should pull out the a. This becomes 0 to infinity of e minus a minus I like this. Okay. And And this becomes, right, if you do the integration of this, not difficult. Because A is a real number, and so you don't need the condition that because A is a real number, IT is a complex number, so you don't need to know whether the condition holds or not. So we know that A is always positive, so the limit at infinity will be 0. And the limit at 0 will be so this will be, so the answer is A divided by A minus IT. So this is the characteristic function of an exponential random variable. Okay, guys. Any questions so far? Or do you find? I mean, you will find this useful because, I mean, the reason I'm doing this is because we have no assessments left for the course I taught you. So I'm trying to teach you something that will be useful for you in year 2. Okay. I mean, all right. So this is example 1. Example 2. Let's look at example 2. Suppose suppose we have a uniform variable 0 to A. All right, now let's see how we can derive the 3 functionals A, starting with the MGF. The MGF is going to be 0 to A, E of Tx times the density, which is 1 over A dx. Okay, so this is going to be 1 over A. You should do the integration of this, which is not difficult, which is okay, this is what you get. Taking the limit, you get 1 over A okay. So you can write this as E of TA minus 1 divided by A T. So this is the moment generating function for the uniform variable. B, all right, B is the probability generating function, which is defined as the expectation of T power X, right? So this is the integral from 0 to A times T to the power X times 1 over A dx. Now, any ideas on how to do this integration? Come on, guys. You did 1 full semester of calculus last semester. So to integrate this, you use the same trick as I said to you before. So you write this as 0 to the power 0 to A, integral of E log of T power X log of T. Okay. Okay, guys. Are you with me? Now, excuse me, sorry, what am I doing? If you do the integration of that, it's going to be 1 over a take the limit from 0 to a. So this is going to be 1 over a. The limit at a is going to be this. Okay. Now, if you really simplify the terms further, put them together, you get this. All right. So this is the probability generating function of a uniform variable. And finally, C is the characteristic function. And so this is going to be the integral from 0 to a of e I t x 1 over a dx. So this is going to be 1 over a. Integral of that is e. So it's going to be 1 over e of I t a. Okay, guys. So I just introduced three I just introduced three different functionals of a random variable and did some examples on those, right? So tomorrow I will talk about more of the stuff that you will learn in probability 2. And then on Wednesday, on Thursday, I will talk about statistical methods, because statistical methods is a course you will take in semester 2 of year 2. So I will talk about some of the things in statistical methods which follow up from the stuff I have done in this course. So please, if you have time, please try to come to the classes tomorrow and the class tomorrow, which is 10 to 11, and the classes day after, which is Thursday, from 11 to noon and 1 to 2. All right, guys. Any questions you have on the stuff we did? Oh, it's not difficult, is it? Well, traditionally, I found that people say probability 2 is difficult, but I hope you won't find it so difficult. All right. Thank you, guys. All right. I'll see you guys tomorrow if you're joining us. All right. So have a great day. I will send you the marks for quiz 10 later today. Okay.